So today we talked a bit more about being able to combine vectors and being able to break things down into x components and y components, because those two things are completely independent of each other, and so we can break things down into those two independent things and then recombine them. Because you cannot combine x's and y's just by adding them. You have to break everything into just x's, break everything into just y's, and then use the Pythagorean theorem to actually combine everything. So if you had two vectors, say that one was over here, and you had another one that was, let's say, over here, and this was maybe 30 degrees, and this was 45 degrees from here, which would make it 180 plus 45 all the way over, or 225 degrees. And you wanted to know what happened when you added those two things together. You'd have to look at the x component of this one and the y component of this one, and compare that to the x component of this one and the y component of this one, add them together, the x's and the y's, and then use the Pythagorean theorem to combine them again. So if we called this vector r and this vector s, then the x component of r is going to be equal to r, and I'll write them as vectors, r times the cosine of 30 degrees. Ry is going to be equal to r sine of 30 degrees. For this one over here, the sx is going to be equal to s times the cosine of 225 degrees, or we could also write that as negative s times the cosine of 45 degrees. We can write it as the short angle here, or we can write it as the full angle, as long as we are taking into account the fact that we are dealing with the direction where the component is facing. Technically, this should have been a sine. So we have the sine of 45 because it is the opposite side over here. And the negative comes into play because it's pointing to the left. You would get that negative out of the cosine of 225. Okay, so then sy is going to be equal to s sine of 225, or if we're looking at the short angle instead, it's going to be negative s times the cosine of 45 degrees. So then you would take the rx's and rs's and put them together. You would take the ry's and the sy and put it together. And then you would have some new vector, or if you call that t, some t vector is going to be equal to rx plus sx, and ty is equal to ry plus sy. Then, to figure out exactly what t is, to get the magnitude of it, then you use the Pythagorean theorem to say you have tx squared plus ty squared with the square root gives you t. And then in order to figure out what angle that is, you take the inverse tangent of ty over tx, the new y over the new x, and that will give you your angle. As long as you know what quadrant you're in. If you're over here, you're going to have to worry about adding 180 degrees. So if you look at your picture and know where things are supposed to go, then you can know if that angle needs to be modified. But it's all about breaking it down into the two completely independent things, the x's and the y's. Because then you can analyze them separately and then put them all back together. Otherwise, you just can't, you cannot do it any other way, except for some other set of 90-degree orthogonal axes. This also means that we can then take our one-dimensional projectile motion and now talk about it in terms of two dimensions if we have both the horizontal movement and we have the vertical movement. And you can treat them completely independently like we were just doing with these different components of the vectors. And so for those projectile motion equations that we had, we can write each one as x's and each one as y's because they are completely separate. So for example, you would have Vx equals V0x plus AXT, and you would separately have Vy is equal to V0y plus AYT. And you have the same modification for the other equations that we were using. These are completely separate. The velocity in y in no way affects the velocity in x. And acceleration in x no way affects anything that's happening in y. Acceleration in y no way at all affects what's happening in x. So if you have some object that you're throwing, okay, and you completely forget air resistance, then it will have some kind of parabolic form where the x motion, the horizontal motion, is the same at the end as it was in the beginning. It's the same in the middle as it was in the beginning, because it's not being changed. There's no a. So Vx is equal to V0x all the time. Nothing is happening. But gravity, we have 9.80 meters per second squared in acceleration down from gravity. So any velocity that was going up here from the y ends up getting smaller and smaller and smaller until at the very top, that velocity in the y is 0, the initial x is still there, and then it becomes more and more negative as gravity brings it down. So it slows it down and then makes it become more and more negative. And it's completely independent. Those two different, the horizontal direction and the vertical direction, are completely independent things, and so we have to treat them completely independently. The motion in one will not affect the motion in the other. Okay. There may be some times when you might have an acceleration in the x direction, like say you have a rocket pack, then, and it's only directed in the x direction, then that you would have to worry about that acceleration being right there. But if you're talking about just plain old something being thrown, where the only acceleration you're experiencing is gravity, the 9.80 meters per second squared down, then you have to worry about the acceleration equations for the y, but everything in the x is just plain old Vx equals V0x, and Vx is equal to delta x over delta t, the plain old definition for velocity. Okay. So we'll be investigating projectile motion a lot more in the next class, but we need to be able to use these vectors to say if I have a velocity right here, that means I have an x component and I have a y component, and what's actually physically affecting it as the object is moving. That's what we'll be investigating.